Hello, Algebra 2 students. This is the second podcast that you're watching for Chapter 9. The first one was in 9.4, and I would recommend that you look back at that video if you need another refresher on that, because the concepts we learned in 9.4 will definitely be helpful for what we're going to learn in 9.5. Now, what we're doing here is shifting between the multiplication and division aspects of rational expressions, and now we're focusing on addition and subtraction. So we're kind of changing the operations that we're focusing on. And then at the end of this lesson, we're going to get more into complex fractions, which involves all the different operations, so it takes a little bit more time, focus, and energy to get through them. To begin, recall from section 9.4 that we had two steps involved in simplifying a rational expression. The first was to factor our numerator and our denominator, and then look for any common factors between the numerator and the denominator and divide them out. And then anything that was left over were uncommon factors between the two parts of the rational expression. So when it comes to adding and subtracting rational expressions, we're going to keep these steps in mind, but we're going to have to be a little bit more in depth with our procedure. And the key difference is we're trying to find the least common denominator. All this is trying to find the parts of the two or three denominators that we're dealing with, find what they have in common, find the differences, and then change our expressions so that we have one common denominator between all of our expressions. So let's get a little bit more in depth into what that means. For the steps for adding and subtracting rational expressions, there's actually 5. The first is the same as last time. We factor the numerator and the denominator of each expression always to start. The next step is determining the least common denominator between all of the denominators you have present. So what I usually do is I find whatever commonalities are there between the denominators, put those in one color, then I give each expression their own color and write down those uncommon factors so that I get one big combination of factors, which would be my least common denominator. We also call that the LCD. Then I would rewrite all the expressions in my giant expression by multiplying the top and bottom by whatever is missing. So if it's in the original color, which I usually use is black, that means it was common between all of them, so I don't have to multiply that. Any color that hasn't been assigned to that expression, those factors are going to get multiplied top and bottom. This sounds a little confusing, but trust me, as we get into the problems and the examples, you'll kind of see what I'm talking about. In the end, you should have all denominators with the same LCD. Then you would go ahead and add and subtract your rational expressions, and we'll talk about that and the misconceptions that can come along with that. But then you would combine the like terms in your numerator. And the last step is just checking to make sure that everything is simplified, so you try to maybe factor your numerator, see if there's any common factors, and cancel those that exist. I could talk all day about how to work through these problems, but unless you see an example, it's not really going to make sense. So for this example, we're going to do some addition of rational expressions. And the first thing that we always do is factor our expressions. So looking at the first one here, we're going to have 3x on top, nothing to factor there. And then we have a difference of 2 squares. So that's going to be x plus 1, x minus 1. And then we're adding our second expression, and that is going to give us 5 on top, nothing we can do there, divided by x, which has already been factored out. And then for x squared plus x minus 2, we're going to have 2 binomial factors, starting with x for both. And then to get a minus 2 and a plus x, we're going to have plus 2 minus 1. So the 2 is bigger, which makes it a positive x value, and then the negative 1 makes that multiplication a negative 2. So now that everything's been factored, we know that this is an equivalent statement, but it's not useful to us yet because our denominators are not the same. So what we're going to do is we're going to look for our LCD, or our least common denominator. And that is going to be whatever's in common. So x minus 1 seems to be the commonality between the two denominators. So x minus 1. And then I'm going to say that this expression is red and this expression is blue. So the parts of our denominator in the red expression that aren't in the blue expression is just x plus 1. And then from the blue expression we have an x times an x plus 2. So this whole thing is eventually going to be the denominator of both of our expressions. And in order to make the denominators the same, we have to multiply each expression by what's missing in the least common denominator. So for our first expression, we're going to multiply it top and bottom by all of our blue factors. So it's going to get x times x plus 2 on top and x times x plus 2 on the bottom. And then with our second expression, we're going to multiply it by everything in red. So x plus 1 over x plus 1. So all we're doing is changing things. We're basically multiplying the expressions by a fancy 1, but now through that process we have the same denominator, which is going to be what we have up here. So I'm going to move the x out front just because it's the simplest factor, and then x minus 1, x plus 1 times x plus 2. As for our numerators, we're going to be adding, so we're going to multiply the first factors together, so this x and this x can become 3x squared times x plus 2 plus 5 times x plus 1, which is 5x plus 5. And remember, we're multiplying all of these things out, we're distributing and foiling, because we want to see if our final polynomial on top can be factored at all. So continuing to distribute, we get 3x cubed plus 6x squared plus 5x plus 5. And then still divided by our original least common denominator. And in this case, our polynomial is not factorable. So this is actually going to be the final form. And in your homework, you probably won't see something as complex as this. You'll probably see things that are easily factorable, and so you might actually be able to cancel things. But in this case, we're just trying to get you to understand the process of adding two rational expressions that don't have the same denominator. With our second example, we're going to do subtraction. So again, we need to factor everything first. So looking at our first expression, we have x plus 2 on top, which can't be factored. Then I'm going to factor out a 3 first before trying to factor this further. So x squared plus 4x plus 4 is left over. And then looking at our second term, looks like we have 1 over a difference of squares. So that would be x plus 2, x minus 2. Now getting back to this first rational expression here, we can actually factor that further, and that's going to give us x plus 2 over 3 x plus 2 times x plus 2. And then minus our x plus 2, or 1 over x plus 2 times x minus 2. Now before we continue, this might actually be a good time to see if there's anything that we can simplify with our two rational expressions before we try to combine them. And indeed, when we look at our first rational expression, we have an x plus 2 and an x plus 2 in our numerator and denominator. So those can cancel. So really we're dealing with a much simpler problem of just 1 over 3 times x plus 2 minus 1 over x plus 2, x minus 2. So now we can figure out what our LCD is. So the LCD, it looks like between the two denominators, x plus 2 is what we have in common. And then from our first expression in red, we just have a 3. And from our second expression in blue, we have x minus 2. So for our first expression, we want to multiply top and bottom by what's in blue, x minus 2 over x minus 2. And our second expression gets multiplied top and bottom by what's in red, so 3 over 3. So we can go ahead and multiply these out. Our least common denominator will be 3x plus 2, x minus 2. And on top we'll have x minus 2 from our first expression, and then a minus 3, since we're subtracting. Had the numerator been more complex in the second expression, we would have had to distribute that negative. So it might have been good to change this to a plus minus 1. And then the only other thing we can do is simplify the numerator to be x minus 5. And there is no x minus 5 term in the denominator, so we can't cancel anything. And therefore we have our final expression. Sometimes we have to deal with a complex fraction, and I kind of touched on this at the beginning of the podcast, but all it is you have a rational expression that contains at least one fraction in a number of places. It could be in the numerator, the denominator, possibly even both. And the key here is that it's at least one fraction, so you could have multiple fractions being added and subtracted in, say, the denominator. This sounds very, very complicated, but we just need to stay calm, focus on it one part at a time, and using the skills that we have learned so far, we should be fine in getting through all this. So I have 2 examples for us to go through, and each of these examples will detail 2 different ways for simplifying these expressions. So for the first example I have for complex fractions, you can see already that not only do we have a fraction in the numerator, but we also are adding 2 rational expressions in the denominator. So to start, we're going to leave the numerator because it's already completely factored and it's just one fraction, and we want to focus on getting that denominator to be one fraction as well. So focusing on that, we will have the top as is, so 3 over x minus 2, and then we're dividing by, now everything's factored in our denominator, so we can look for our LCD right away. The LCD is going to be x minus 2 from the first rational expression and 3x from the second. Don't really have to color code here because it's pretty simple. We can keep track of our factors pretty easily in this one. So I know that I need to multiply top and bottom here by 3x over 3x, and top and bottom on the second one by x minus 2 over x minus 2. When I do this, I get 15x plus x minus 2, so just multiplying the 1 times the x minus 2, and then our common denominator is 3x times x minus 2. Remember, this is still the main rational expression we're dealing with, so there's still division involved. But now we have 3 over x minus 2 divided by 16x minus 2 over 3x x minus 2. When you're dividing by a rational expression, as we discussed in 9.4, you actually want to flip the numerator and denominator and multiply. So in this case, we're going to have 3 over x minus 2 times 3x x minus 2 all over 16x minus 2. And you may have recognized that 16x minus 2 can be factored further, and we will go ahead and do that in the next step. So 3 times 3x times x minus 2 gives us 9x times x minus 2. And then our denominator is x minus 2. We can factor out a 2, and then we have 8x minus 1. So the final step for simplifying, of course, is to find our common factors between the numerator and the denominator. We can cancel those out, and then we're left with 9x over 2 8x minus 1. So the keys here were determining what we wanted to tackle first, which was our denominator, and that involved adding rational expressions, so we had to find a least common denominator. And then once we had one fraction in the numerator and one fraction in the denominator, we could go ahead and simplify the way that we learned in 9.4. Our second example for complex fractions actually involves a different process of simplifying. So here we have a word problem where the focal length of a thin camera lens is given by the following expression, and we need to simplify this complex fraction. So the step for this one actually is determining what our LCD is between the different expressions in our denominator, and then we're going to multiply top and bottom by that common denominator. So in this case, the LCD is going to just be PQ. So if I multiply top and bottom by PQ, I'm going to get PQ all over PQ times our original denominator. So when I distribute that PQ, we're actually going to get PQ all over P plus PQ over Q. And you can see that in the denominator we actually have, with our two rational expressions, common factors in each. So the P's are going to cancel in the first expression, and the Q's are going to cancel in the second one. And that just leaves us with PQ over Q plus P. And this is the most simplified form of this original expression. So we didn't have to find a least common denominator to combine the expressions in the denominator. We actually just used it and multiplied everything, top and bottom, by that LCD and then simplified accordingly. So to recap, there are indeed two different methods for simplifying complex fractions. The first one we used involved writing the numerator and denominator of the main rational expression, and then dividing and canceling the common factors. And then with the second one, we multiplied the numerator and denominator by the LCD of every fraction in the numerator and denominator, and then simplified accordingly. So you may want to go back and look at those two examples again to see how those two methods differ and yet arrive at the same conclusion. So, for example, you might look at example 3 and try the second method to simplify, or maybe look at the second example, example 4, and use the first method, and you should see that you would get the same simplified expression. Okay, so similar to the first video, I have some tasks for you to complete before next class. First one is to, again, just watch this podcast like you already have, and then rewatch it. Again, you don't have to take notes, but they may be helpful for your homework. And I want you to write down those 1 or 2 questions you might have about it. We covered a lot in this section, so you might have questions about finding the least common denominator, or adding or subtracting, or, as most of you will probably have, questions about those complex fractions. And we will go through those concepts and examples in class to make sure you're all clear about that. And then we discussed in class the E equals MC squared problems for 9.4, and you got a chance in class to work on those. For this section, I actually want you to try to attempt those problems before coming to the next class. So work on those problems. You don't have to finish them per se yet, but I want you to work on them, see how far you can get, because I am going to ask some people to come up and present how they completed the problem. And if you weren't able to complete the problem, I do want you to kind of make a note of where you got stuck, why you got stuck, if that happens, and then in our class discussion, we're going to clear up any confusion you have about those problems so that hopefully the homework will be smooth sailing.